All right, let's get started. Happy Valentine's Day, everybody. Let me get the sign-in sheet passed around. See, I've put hearts on the announcement slide. You can tell I'm festive. Couple things. You currently have a homework that you're working on, homework number 4. That's not due till next week, so you have plenty of time on it. You can do problem 1 right now. After today, you'll be able to do problem 2. And honestly, if you gave problem 3 a stab, you could probably get a fair chunk of it done. But definitely after Monday, problem 3 will make a lot more sense. Before we get into the lecture, a couple other things. So when it comes to your homeworks, homework 1 has been graded and returned. The solution should be active on Blackboard. Homework number 2 is currently being graded. Like I said, that was a big one. If you haven't gotten it back by Monday, I'm giving you the solution on Monday, so don't worry about that. Homework number 3, obviously, we'll get to that after homework 2. I think that one will be a little quicker from a grading perspective. So yeah, but I will make sure that you all have solutions to the homeworks well in advance of the exam. So yeah. I know my TA's got a lot of these grading right now. So, sound good? Okay. So, what we're going to do today is we're going to do known cross-section design, and that's a lot easier than unknown cross-section design because there's a lot, there's much fewer parameters that you need to assess when you have a known cross-section. Remember that known cross-section design really comes from 2 places. Either you're using an element that's precast, so you already know what the dimensions are, and so all you need to determine is how much reinforcement is in there, or you're designing a slab. And there are some details with slabs that will become a little bit more important later, but that's basically that in a nutshell. Now, I'm going to show an equation here in a second, but I want to go back a little bit and see if you all remember where this equation came from. So if you recall, when we first started talking about design in general, we introduced this term of a reinforcement ratio. This area of steel is rho BD. And one of the things that we did with this reinforcement ratio is we used it to sort of rewrite what the capacity of a section is, right? So we said, okay, how do you determine the moment capacity? Well, you say C equals T, and you use that expression or that concept of equilibrium to solve for A. And so for a rectangular beam, A is ASFY over 0.85 FC prime B. And then because I've got this new term for area of steel is rho BD, I substituted that into where I got a new term for A. And then if your moment capacity is ASFY D minus A over 2, do similar substitutions. Area of steel is rho BD, and A over 2 is this expression here. I can reformulate that a bit until I can come up with this box. And I use that box and that expression because that expression is really, really critical. It tells me what the moment capacity is as a function of the dimensions of the beam, the material properties, and rho. Okay, so if I know what the beam looks like, and I know what my material properties are, all I need is rho, and it tells me what the capacity is. And that should be kind of telling because if I'm designing a known cross-section, you would think that this expression is really, really important. And guess what? It is. Now, the point we made about it last time was we were trying to make just a conceptual point about design economy, that if you keep throwing steel into the cross-section, yeah, I mean, you'll up the nominal moment capacity, but you really won't increase your usable capacity. Because of phi, because of your resistance factor, there's sort of a point where you keep throwing steel into the section and it doesn't really matter, okay? So that was the point we made last time, but what I'm going to do now is I'm actually going to use that expression much more explicitly, okay? So we skipped past all this, we looked at reinforcement ratios, then we came up with design for unknown cross-sections, and now we're here, we're designing a known cross-section, okay? So again, if I've got a precast element or I'm looking at a slab, really all I have to do is solve for the steel. In other words, I need to solve for the reinforcement ratio. So what do I mean by that? What do I mean by solving for the reinforcement ratio? Well, I'm going back to this equation. This is the equation that we just looked at. This is the nominal moment capacity equals a pile of junk. And what's over on the other side of that pile of junk? Your material properties, your FC prime and your FY, which you can assume at the beginning. the beam dimensions, B and D, but if it's a precast segment or if it's a slab, you'll know what B and D is because you know what the cross-section looks like, and rho. So all I'm going to do is take that expression and solve for rho, okay? So the next slide is just a little bit of algebra, okay? So bless you. So here's what I got going on. So if you look at what I've got here, so started out with this equation, so started out, that's right there, and then I'm solving for rho, okay? So rho is what I want. Rho equals something, okay? So let's divide both sides by this pile of junk here, this FYBD squared, and so I get this. So Mn over FYBD squared equals this. And then let's collect everything all over to one side of the equation. So what I'll do is I'll add this over here, and I'll subtract that over here. And that equation right there may look kind of messy, but think about what's going on. I've got a pile of junk times rho squared plus a pile of junk times rho plus another pile of junk equals 0. And I can start filling this in, right? Because the pile of junk times rho squared is Fy over 1.7 Fc prime, and this is minus 1, and this is Mn over FYBD squared, but should be somewhat recognizable, right? That's just a quadratic equation, right? Pile of junk times rho squared plus a pile of junk times rho plus a pile of junk. So you could sort of treat it as ax squared plus bx plus c equals 0, only instead of x we're solving for rho, right? So how would you solve this expression? Well, Pythagorean Theorem, right? X equals, or rho in this case equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Okay, well, when you do that, a couple of things. First off, the algebra gets a little messy, right? As I'm sure that you would expect, just looking at the terms. So what I have here down below is the answer. This is just me taking this, solving the quadratic equation, and prettying it up a bit with, with all the algebra. Okay, so that would be point 1. But point 2 is, okay, if I look at the quadratic equation tells me that rho equals negative b plus or minus, right? Square root of over 2a. In other words, there's 2 answers, right? So why do I only have 1? Well, the reason I only have 1 is because when you look at this quadratic expression and you solve it out, you're only going to get one answer that's positive, okay? So you know how quadratic equations work. You can get one positive answer and one negative answer, right? So think about what we're solving for. We're solving for a reinforcement ratio. So a negative reinforcement ratio really wouldn't make any sense, right? I wouldn't design a beam and say, okay, it needs negative 3 square inches of steel. That doesn't make sense. So we only take the solution that yields the positive value. So all I'm doing is I'm taking this expression, solving for rho, only taking the positive answer, and reworking the algebra to come up with this. That's all that is, okay? So if you want, you're more than welcome to do this yourself, and you'll come up with the same answer, okay? Now, it's not a typo here. It's 1 minus the square root of 1 minus. So that's not a typo, okay? That is how that's supposed to be, okay? Another thing about reinforcement ratios, what are the units for reinforcement ratios?
Unitless.
They are unitless. There are no units. They're a percentage, right? So make sure that the stuff that you plug into the reinforcement ratio makes sense, okay? So, for instance, if you have FC prime and KSI, and this is in inches and this is in inches, your moments need to be in inch kips, okay, not foot kips. Okay, so just be aware of that. And again, this is a whole lot different than the 0.18 FC prime over Fy or some of the other expressions that we're using, because here, because we have a known cross-section, we're solving for the steel. We're not having to make some guess to get a cross-section. Make sense? Okay, so your procedure is very similar to what we looked at last time, but there's a lot less steps in the middle because we don't have to solve for a B or D. We don't have to figure that out because we know what that is. So the first step is to compute the factored moments, but that also is a little bit easier. In the unknown cross-section design situation, you don't know what the beam looks like. So because you don't know what the beam looks like, you have to guess what the beam looks like, which means you have to assume how heavy it is. But if you know what the beam looks like, then you don't have to do that, okay? You know you can compute it directly. Now you do still have to assume that phi is 0.9 because your phi value is a function of how much, it's the strain in the steel, and you don't quite know what the strain in the steel is if you don't know what the steel is. You haven't picked it yet. So that is technically an assumption that you would need to go back and check later. So we'll take Mn is mu over 0.9, and then now that we have an Mn, we can just plug it in right there. A little bit of a nasty expression, but it is pretty plug and chug. And then we just take rho BD, pick a reinforcement pattern just like we did last time, and then go back and analyze the section to verify our assumptions. And when I say assumptions, they're really the only assumption that we made is that phi equals 0.9. So we would want to verify that. We would also want to verify that we met the minimum steel requirement and that we met our strength requirements. Sound good? Okay. So I want to go through this problem here. This is it's going to be a lot quicker than the last problem that we did. The last problem we did was long. There was a lot of steps to it. There's a reason why on your homework assignment, problem 1 is worth like 15 points, but the rest of the problems are worth 10 points because problem 1 is a long problem. This one's going to be a lot shorter. Okay? Now, we'll need your help with this one. We're going to select the reinforcing steel for the rectangular cross-section shown. So, I'm also telling you what the moment is. Now, if I didn't tell you what the moment is, I instead would be giving you, okay, the beam is this long, it's simply supported, or it's cantilevered, there's these loads on it. I just told you that MU is 160 foot kips. That makes things a lot easier. And we're going to use 3 KSI concrete, 60 KSI steel. We already got the beam dimensions. It's a 16-inch wide beam. Its effective depth is 21 inches. Note that I didn't give you the height of the beam, but that doesn't matter because the height of the beam would only be used in one place, and that's to compute the self-weight of the beam. And the self-weight of the beam is used to compute factored moments. I already told you what factored moments are, so that's really not needed. Okay? So really all I want is that. I just want the area of steel. Sound good? All right, so let me, so 3 KSI concrete, 60 KSI steel, and it was 160 foot kips. Now, if 3 KSI is our concrete capacity, what does that tell us about beta 1? 0.85. Remember, it's 0.85 if it's anything less than 4 KSI, anything 4 KSI or less. So it's still 0.85 here. It's only 0.8 if it's 5 KSI, anything higher than 4 KSI. Okay, so that's our beam, and so all we're doing is solving for the area. Okay? All right. Now, step 1 says to compute factored moments. But we were given that. MU is 160 foot kips. So that step's done. There's really nothing to do there. And again, I'm just trying to make the problem a little simpler for us to do in class. I mean, you all can, I would hope, can do that because that was the whole point of structural analysis last semester. Okay. Step 2, compute required nominal moment capacity. All right, so MN required is MU over phi. And so, what do I got to do here? I have to assume that phi feet is 0.9. So 160 foot kips over 0.9. Somebody help me out with that.
21, 33.33.
Wait.
Oh, no. I did it.
You did it to inch kips? That's going to come next, yeah. What is this one? Because I want to follow that out. But you're ultimately right. He was listening to me earlier. I like that.
177.7.
So this is 177.7 foot kips. Do I have a second on that?
Yeah, 0.8.
Uh-oh. I think you just, there's a couple people who should have, you got outvoted. We're going to go with 0.8 because I'm telling you, that is going to affect the design. I mean, I'm kidding. You know, you do have to be. Okay, so now, Mr. Atkins, what were you saying? So it was 2133.3 inch kits?
Yes.
Okay. So what he did is he converted that to inch kits because if you remember what I said earlier, when we plug this into our row expression, all our beam dimensions are in inches, all our material capacities are in KSI. So the moment needs to be in inch kips so that everything matches from a units perspective. And I'll go ahead and tell you, in design mode, just a lot of time, like usually in design mode, you kind of have to pick a force unit and pick a length unit and go with it. And when you're dealing with stresses and moments, like inches and kips tend to work pretty well for US units. So, because if you work with inches and pounds, the numbers get really, really high, you know, like 29 million PSI for your E value and things like that. So I've always work in inches and kips, so when I'm in design mode. Okay. So, step 3, compute required reinforcement ratio. Let's see how I do. So, rho required is 0.85 FC prime over Fy, 1 minus square root 1 minus 0.85 FC prime BD squared 2 MN. Is that right? Get any typos? How did I do? I'm asking you. I'm not even going to pull up the slides. I'm pretty sure that's right. Did I get it right? Okay, good. All right. Well, I'm trusting you. Okay, so now we've got this expression, and part of the purpose of this example is just to get used with this formula because it's really big. So I just want to make sure that everybody can compute this out. Okay, so 0.85, 3 KSI over 60 KSI, 1 minus, and then 0.85, 3 KSI, 16 inches, 21 inches. Don't forget to square the depth on the bottom there. And then that's 2 times 21, 33.3 inch kips. All right, so so again, the formula is nasty, but does anybody remember something about rho values when you compute them? They're small. They're small numbers. So when you get a number, it's okay if it comes out small. In fact, that's kind of what you want. So give me something like 5 decimal places, because rho values, because they're small, you want specificity with it. Say 5, because again, these are I want this to have some specificity. It's 0 point something, or at least it better be. It's okay, take your time. This is a nasty one. Again, don't forget to square the D on the bottom. That's a common thing to forget, is that that 21 is squared.
0.005379.4.
So 538. Do I have a second on that?
Yeah.
That sounds about right. And so if you're not getting that, check your squared here. Check the 1 minus, so it's 1 minus the square root of 1 minus. Okay, check that. Let's see. Check that you're using the right moment, that it's the inch kips one and not the foot kips one. And just check, your signs all around. So, everybody good? So, if that's, I'd kind of say that's the hard part with this problem. Everything else I think, I don't want to say boring, but it's pretty simple. So, step 4, compute required steel area. So now that I have a row, I can say AS required is just row BD. And so what does that come out to be? Say it again?
1.81.
1.81 square inches, right? Do I have a second on that? Okay, so we have an area of steel, I guess minimum, of 1.81 square inches, and the beam is 16 inches wide. Okay. Now, let's go back to, let me do it like this. Put that on this. Okay. Let's go back to this. Okay. So let's see if let's just do this together on the board, because this is pretty simple, I think, at this point. Let's start picking some bar sizes. The number of bars, and then B minimum. To come up with some options that we think would work and make sense. So, I don't know, let's start off with, I don't know, maybe number 5s. How many number 5s would we need? 6 of them, right? Okay, 6 of them, that would give me an area of what, 1.84? What's the beam width required? Does anybody have that on? It's down below. 13.38. That's an option, right? Did I get that right? 13.38? That's okay. All right. What about, maybe we ought to go a little smaller. What about number 4s? How many number 4s would we need?
11.
No, is it, hold on. 9 is 1.77. 10 is 1.96. We need 10, right? Good. Like, so, yeah, 1.77, 1.96. I know that can be a little weird to see. Now, what's the beam width? Oh, that's square inches. What's the beam width on that one? Anybody have that on them, or do I need to scroll up and down? I prefer not to have to scroll up and down. If I have 10 number 4s, and so, yeah, okay, let's talk about that.
Do we add for each additional layer?
Exactly.
This is 17.64.
All right, so number 4s, well, now hold on, so number 4,
Oh, no, yeah, I
we have number 4s, okay, so this is important, okay, so we have 15.75, that's for 8 bars, plus 2 additional layers at 1.5, so that's
just for
18.75, is that a feasible option? No, no. So we probably don't need to look at number 3s, right? So maybe what we ought to do now is we look at number 6s. All right, so what do we got for number 6s? 5 of them. All right, let's just go ahead and do all the other bar patterns. What about number 7s? Number 7s, we would need what? 4? Um, 2.41. All right, number 8s. Well, actually, before we start writing this out, let's see what happens here. Okay. Well, let's write this out. So 3, 2 point. This is 2.36. Let me ask you a question. Should I really waste my energy checking to see whether or not these have fit? You're shaking your head no. Why?
You want it to be as close as possible to your man or house is cheap.
Exactly. So this fits, right? This fits, and I have 1.84 square inches of steel, right? All of these, even if they fit, are heavier than this option, right? This is the lightest option, right? Are there any other options that would be as economical as this one? Maybe. Bless you. I mean, I got the number 9s. I could do 2, but that's 1.84. 2.55, that's 1.84. 3.13. None of them are lighter than this one, right? None of them. So, therefore, for this problem, so if you want, you can say, all right, 5, select reinforcement pattern. Use 6 number 5s, okay? And I'm going to call that a preliminary answer. I'm going to call that a preliminary answer because my final step is to always check this answer, right? So, when I say analyze, trial section, I'm after 3 things, okay? I'm always after 3 things. The first thing I want to do is verify my assumptions. I.e. B equals 0.9, right? That's the first thing I want to do. The second thing I want to do is compute efficiency mu over VMN, and 3, check ACI requirements. And for beams, there are 2 ACI requirements. One of them you're going to kind of check anyways, because one of them is a check on the strain. The strain has to be higher than a certain value. If the strain is higher than that value, then phi equals 0.9. So you're going to check that one regardless. What's the other ACI limit on beams?
Minimum steel.
The minimum steel reinforcement requirement. So there you go. Now with efficiency, we're going to take MU over phi MN. Computing MN, or phi MN, that's a little bit of a task, right? Because we've got to compute A, we've got to compute MN, then you've got to compute C, the strain in the steel to determine what your phi is, and so on and so forth. All right, when you get your efficiency, what's a good number for that value? What do you want it to be?
90%.
90% or higher, but not over 100%, right? If it's over 100%, that means there's more load than resistance and the beam fails. Okay? Now, I'm not going to do this for you right now for the simple fact that we literally have done this how many times? You know what I mean? So I'm not going to do that. Okay? Sound good? All right. Now, any questions? All right, I'm pretty sure I need to upload the slab design notes. I haven't done that yet, but that's okay. I can do that today, and then we'll have those notes for Monday. So today we can treat this a little like movie time. What I want to do now is I want to talk about slabs. Okay, now what I mean by slab, I don't mean the slab in your garage. Okay, and I don't mean this. Okay, because we're on the first floor. Okay, so this slab is on the ground. Okay, I'm talking about freestanding slabs in buildings. I'm talking about that slab up there. Okay, the one holding up the second story, and the third story, and the fourth story. Okay, the reason I'm talking about this is because I kind of want to get you to understand this. Okay, if there's any one goal that I have for reinforced concrete design, it would be your ability to design that. Okay, what is that? That is a floor system in a typical building. Okay, and if you notice, there's beams and girders, which we've been talking about beams and girders. Okay, but that's not it. There's the slab in between. Okay. So we need to talk about designing the slab in between. Okay? Now, if you notice, I didn't really mention this, but I said one-way slab design. What do I mean by one-way slabs? Okay? One-way slabs are designed to bend one way. Okay? So whenever you are looking at structural design, you ever hear the term one-way slab, they are designed assuming that they only bend in one way and that they behave kind of like a beam, okay? Another more complex design would be designing a two-way slab. Two-way slabs don't bend just one way. They kind of bend this way and that way, okay? The analogy that I can think of is, imagine you treated your slab as if it was like a square trampoline. And so it kind of just bends in all different directions, okay? The mathematics associated with designing a two-way slab are a little bit trickier, okay? If you wanted to talk about the pure structural analysis, you go from like ordinary differential equations to partial differential equations. You're talking about plate analysis, and it gets a little messy. There are some ACI methods that make two-way slab design a little bit easier, but in order to crawl, or in order to walk, you got to crawl first. So we're going to do one-way slabs. Now, are two-way slabs used all over the place? Oh yeah, they are used quite a bit. I'll give you two examples where two-way slabs are used. Two-way slabs are generally thinner. They're generally, because you can transfer the stress in different directions. A two-way slab can be thinner. That's sort of the whole reason that you would do it. It's like, why would you make the problem more complicated? Why wouldn't you keep it simple like a one-way slab? Well, there's got to be a reason. Two-way slabs are thinner. So, for instance, if you go to Washington, D.C., okay, there's a city ordinance that says that any structure that you build in Washington, D.C. has a height limit. In other words, it can't be taller than something. What do you think that something is in Washington, D.C.? Anybody been to Washington, D.C.? There's a big tall thing in Washington, D.C. The monument. Nothing in Washington, D.C. can be taller than the monument, okay? So now let's say you're a spec office space developer and you want to build a building, right? Okay? You're wanting to charge people rent to occupy that building, right? It's sort of like, you know, when you go to the mall and there's like a Banana Republic or a GameStop or something. They pay rent to the mall on a per square foot basis, right? They rent so many square feet of mall space, and that's how they're charged rent. So the bigger the store, the more they owe rent, okay? And it's the same thing here, right? If you have a big commercial office building and you're going to have lawyers and doctors and government agencies and all sorts of stuff occupying that building, you as the developer want as much square footage in that building as you can, because the more square footage you can rent out, right, the more money you make. Make sense? So imagine if I could take my floor system and I could go from this with a one-way slab to this with a two-way slab. That doesn't seem like a lot, but imagine I have a height limit in Washington, D.C., and so I only have so many stories. Well, maybe this to this doesn't mean much, but maybe after 30 stories, I save so much height I can put another story in the building. Another story in the building, that's a whole another, few hundred square foot I can rent out and make some money. So that's a very real application. If you want an application a little closer to home, there's a two-way slab actually on campus, and it's in Drinko. The floor system in Drinko is a two-way slab. In fact, it's what's called a waffle slab. Like if you're ever in the guts of Drinko and you see the slab, it looks like a waffle. Like, you know how waffles have like those, like the square pockets, sort of like a honeycomb, but it's not hexagons, it's squares, right? So that's actually what the slab system in Drinko looks like, because those ribs, if you will, are distributing load this way and this way. And you kind of need that for a system like Drinko, because the floor load in Drinko is something like 150 pounds per square foot, versus in here, where the floor load is only going to be like 50 pounds per square foot. Why is the floor load in Drinko so much higher? The books, right? Because college students don't read books, so they just... I'm joking. Am I? I don't know.
I don't read books.
Read something. I mean, you don't have to read all this engineering stuff all the time. Read something. But in all seriousness, the books add significant weight. So another thing about two-way slabs is they can be a bit thinner, but they can also be a lot stronger. So sometimes if you've got a hefty system and you want an open space, a two-way slab might need to be the way to go. Make sense? Okay. So let's talk about slab design. I'm going to talk about one-way slab design. So when we're talking about a one-way slab, what we're talking about is I've got a beam supporting that slab, and we're talking about designing the slab in between. So that's actually what we're walking on in the building. Now, I told you that slab design is a known cross-section design. The reason that it's a known cross-section design is that you can very, very easily determine what the dimensions of the slab need to be. For example, here's my beam, and we'll assume that so I've got a beam here and a beam here. We'll assume those beams go forever, and I'm designing the slab in between them. So what I do in slab design is I look at a small strip of that slab. Typically, we take the strip to be 12 inches wide, like 1 foot of slab. And we'll design, okay, what is the deal with the reinforcement inside that 1 foot strip? And so whatever we get, we just repeat it all the way down the slab. So we take this one strip of the slab, design it, and just repeat the reinforcement everywhere. So from a known cross-section standpoint, we know how wide the beam is. Make sense? We know how wide it is. As for how deep it is, we just get that from ACI limits. So, because we tend to make slabs as thin as possible. So we know how wide it is. We know how deep it is. There you go. Now, one other thing about slabs. Remember with beams, we would say that the difference between the effective depth and the height of the beam was 3 inches. Well, for slabs, we'll typically take that to be something like 1 inch, because your cover for slabs is much less stringent. For beams, you have this 1.5 inch cover requirement. You got all these stirrups and whatnot. But for slabs, your cover is only 3/4 of an inch. You don't really have to worry so much about stirrups. So we can typically take the height to be the D plus 1 inch. So there you go. So, and again, like I said, the slab thickness values come straight out of ACI. So if you have a simply supported slab, we'll just take the length over 20 and the length, and there's your height. Take that minus 1 inch and there's your depth, or your effective depth. So it's pretty simple to determine the depth and then also your quote-unquote width. Any questions? Okay, let me show you the procedure. Again, this is really, really easy if you understood what we just did. Now, we're going to compute the factored moments on the beam, but again, because this is a known cross-section problem, we don't need to assume the self-weight, okay? We will assume phi equals 0.9. We will need to go check that. We calculate a rho for design purposes. AS is rho BD. Now, there's something new here, okay? This is a little different. Notice how we've got, ooh, I've got a typo there. I need to fix that. I'm going to fix that before I upload it. This is supposed to be T, so that's supposed to be AT. Min is 0.0018 BH. Sorry about that. I'll fix that before I upload it. But there are two formulas here for reinforcement. So wait a minute. Beams, we only have the one. We just computed the area of steel. So what's this other thing? All right. Well, with slabs, when you're designing a slab, you have reinforcement going this way, but you also have reinforcement going the other way. Okay. One direction is to actually resist the load, to actually hold up the slab and make sure that it can support whatever load that's on it. That's what the AS is. The AT is what's called temperature reinforcement. So remember how, okay, remember we talked, for those of you that aren't in steel design, we talked, was it last week, about what happened on 64, the expansion joint and all that? Well, related to that, buildings expand and contract. Slabs expand and contract under thermal load, under shrinkage and temperature changes and things like that. Well, slabs, by their very nature, are inherently thin. Okay? Because of that, they're much more susceptible to cracking under thermal changes and under shrinkage and so on and so forth. So we add another layer of steel acting in the other direction. Okay? So, excuse me. So we'll have the area of steel required for the structural capacity, but then we have the temperature steel required to prevent cracking under thermal expansion. So we call that main steel and temperature steel. Okay? But the process is very, very similar. Sound good? All right. We have a couple other requirements with one-way slabs, and I don't really want to get into that today because we'll have a full-blown example next time. But one of the things with slab reinforcement is that the table that we use and the guide that we use is a little bit different. We don't use this guide here. I want to show you the guide that we use. And I'll print off hard copies for you next time. I'll show you an old one because I want to reformat this a bit. So this is, so if you remember, I gave you all the beam design aid. Well, there's a slab design aid. Okay. Now, let me explain what this is. Okay. What this will tell you is the area of steel per foot of the slab dependent upon a given bar size and a given bar spacing. Okay. Let me ask you a question. Let's pick out the number 5 bar. What is the area of a single number 5 bar? Right there. I'm just using a number 5 as an example. 0.31 inches. Okay, inches squared. So the area of a single number 5 is 0.31 square inches. Is that a fair statement? Okay. So what we've got here is a table that shows the area of bars per foot. So I want to look at this row right here, this row. Okay, so this row is when the spacing is at 12 inches. Okay, so when the spacing is at 12 inches, it's saying the area is 0.31. Okay, so imagine that I've got a slab and I put a number 5 every 12 inches, right? Any random 12-inch width is going to have 0.31 square inches. Does that make sense? Okay. Now, that's this row with 12. What about the 6? What about this? What does it say? It says 0.61. It's rounded because of pi and all that, but it's a little bit higher. The reason why it's higher is instead of spacing the bars at 12 inches, I'm spacing them at 6 inches, right? So within a given 12-inch width, there's not one bar, there's 2. So the area increases per foot. Does that make sense? So what this is just the area per foot of a given bar based on a given bar spacing. Does that make sense? So what you'll do is you'll go in and you'll say, okay, I need this steel, find the pattern that gets me as close as possible. Now there's a lot more resolution with slab design than there is with beam design. What I mean by that is, remember here where we had like 1.84 and then it was like 2.21 and then 2.41, like there was a big gap between those numbers. Whereas here, you can see I got a 0.72, a 0.71, you know what I mean? If you look at your efficiencies for slab design, like the efficiencies will be like 98%, 99%, because you can get slab design to be a very, very efficient design, okay? That'll become clear next time when we do a problem. I want to show you that problem real quick. So I got a slab that we're going to design starting Monday. It's going to be a one-way slab. We're going to say that the span length is 10 feet. Now, when I say span length for slabs, what I'm actually talking about is the distance between the beams, okay? Because the slab goes between the beams. So the span length for a slab is the girder spacing for the beams, right? So it's, you got to sort of think three-dimensionally. Now we're going to use regular old concrete, regular old rebar, but we're going to put a lot of live load on this slab. It's going to have 200 pounds per square foot, and the only dead load is going to be the slab's self-weight, okay? So this problem is going to be very, very simple from a design standpoint. What's, I think, the most difficult is just understanding the structural analysis. Like, it's not hard after you've done it one time, but it's, you gotta really think about what's going on. Make sense? Next time I will provide hard copies of the slab design aid. I'll also upload these and fix that that formula for the temperature reinforcement. And then once we finish this example, that is it for exam 1. What we're going to do after exam 1 is we're going to look at flanged sections. And so what I mean by flanged section is instead of a beam like this, we're going to look at this. Or, something like that. So actually putting a top flange. So basically T-beams and L-beams, although they're handled basically the same way. The formulas and the expressions get a lot trickier. Okay? They get a lot longer. And this is going to be exam 2 length. But, I mean, it's all going to relate as well. All right, that's all I have for everybody. If you are done, or if you don't have me for steel design, hope you all have a wonderful Valentine's Day. I'll see you here in a few minutes.